Hi there, Science 9. So today we're going to cover Lesson 2 and later on Lesson 3 of your matter cycles unit. So the other day, of course, I had that brief lesson for Lesson 1. And I've also introduced you to your ecosystem in a jar project. At this point, I'm hoping that most of you are at a point where you've got your jar and you're working on that lab, getting those materials in there, recording everything you can about what goes in there. And remember, you're adding stuff, mindful of hoping that that can survive in there for as long as the jar is sealed with a light source. So check out the online resources for that and have fun. I think you really can enjoy this. And as I said, I've seen examples of this project that have been in people's windows for, well, years, really. And there's the one online resource that has a person who's got one of them that's 50 years old. As long as there's a source of light, the plants inside there can keep growing and provide food for whatever it is else that's using those resources. So that's called an ecosystem in a jar. I defined for you what an ecosystem was. Moving forward, I want us to be getting more into the cycles part of this, but also looking at processes that happen over the entire Earth, some of which we can keep doing, others of which we maybe cannot keep doing as much as we have. Here is, by the way, Lesson 2. So you'll see that I'm hoping that you'll be able to fill in what an ecosystem service is, what is sustainability, and to fit in the diagram I made here. I hope you can at least take notes on the topic. So what is an ecosystem service? For this, I think it's almost best to sort of think of a really concrete example. And the one that keeps coming to me is that of salmon. Here we live in the Bulkley Valley. We're used to the salmon coming every year. Different species come up the Bulkley. People fish for them. Other people fly in order to fish for them, and it's traditionally been a very important food source for the people here, and still is for a lot of people. But the salmon are something that we shouldn't take for granted. They have a lot of requirements in the environment that, well, we can only hope will be met. Salmon need fresh water, of course. They also need clean water. The water has to be cool and clear. For the water to be cool and clear, it needs to be filtered by the soil, which is an ecosystem service that is provided naturally by the soil. For the salmon as well, also it's for us. They need to have cool water, which means that where they're going to be spawning, typically those creeks are going to be lined with trees. The trees hold the soil from going into the water and making it cloudy, and they also keep the water cooler so the eggs don't die. Within the ocean, obviously they need to be fed. The thing about salmon is, well, they feed on a lot of small things called plankton, and the plankton require really tight chemical conditions to survive, and therefore to be able to feed the salmon. I'm going to get into that a little bit on the topic of ocean acidification. We could go on about requirements that the salmon have for their life cycles, but ultimately it all comes back to water that is clean, air that is clean, a food source, certain structures in the habitat that are available, all of which are provided by other living and non-living parts of the environment. Services provided by an ecosystem are required for ecosystems to operate, and there are things that ecosystems can do for us, like keep our water clean, like provide us with new medications or new medicines that are sometimes being discovered in plants in rainforests especially. Now, also another definition I want you to be familiar with is this whole concept of sustainable versus unsustainable. You may already know this, that a sustainable activity is one that people can do, but one that even if you are doing that activity, if you are doing it at a certain level or a certain kind of activity in the environment, in the future, you can keep doing it. An example, key example would be farming. If in farming you're not using too much of your water, maybe you're letting some of that water flow down into the ocean and carry away pollutants from the land. If you don't use too much water, then you end up with over the long term that your farming practices will be more sustainable, and you'll keep from drying out your soil. I'm sure I could come up with better examples than that because I'm not a farmer or anything like that. Certainly around here, a really concrete example would be in forestry. Forestry can be practiced sustainably, and it can be practiced unsustainably. If you were to practice forestry unsustainably, we can imagine having a situation where you have a tract of forest, a large region of forest, and the managers of a mill have decided, well, we want to have boards created at this rate so we can supply our buyers. And they say, okay, and we need to cut this much forest every year to make that happen. Well, what if there's not enough forest to make that happen? What if the natural regrowth rate of the forest doesn't justify that rate of cut? Well, that would make that unsustainable. Eventually, they would run out of trees, and the mill would have to shut down for a lack of wood. Conversely, on the other hand, we can imagine situations where a professional forester is hired by the mill or by a government or by both, and they're able to make statements about what rate of cut can the mill call on. What rate of cut can happen in this region, and therefore that's going to affect how much wood the mill can make, how much lumber the mill can produce. So some activities, mind you, are even by their own nature not sustainable, or any level of that activity is harmful. The first example that comes to my mind would be some ways that gold is extracted from the environment. In some countries, gold is only they get gold from it's called alluvial gold. It comes from streams. Like gold panners will get gold from the sand and from gravel. Well, in some countries where they get gold from sand and gravel and streams, it's present in small amounts, and it's hard to find. So what they do is they use what's called mercury. It's an element which they pass through the slurry, and what it does is it dissolves the gold into it, and then they cook off the mercury. They recover the mercury, and then they separate it from the gold. Downside to that, of course, is that not only does it cost energy to recover that mercury, to undo that mixture, but some of that mercury ends up getting into the environment. And guess what? Mercury in the environment is really, really bad. It's extremely harmful to aquatic ecosystems. So that would be an unsustainable practice, using mercury to extract gold from fresh water. Unsustainable. But of course, closer to home, we know that we have some fossil fuel industries that, in the sense that we're going to run out of this eventually, it's not sustainable. It's not a sustainable practice. Is it one that we can plan for and use at a very low rate, and it'll be present for a very long time into the future? Definitely yes. But it's not a renewable resource. Now, the other thing I wanted to talk about for this is this concept of ecosystem or planetary boundaries. I have this as notes to create at the bottom right here of the page, and I'll show you what I wrote down. You could do a search for this. In fact, I will show you the guy's name, and you can do an image search, no problem. Here it is. Johan Rockstrom, the tipping points. That's what I Googled to find this, or maybe actually I Googled planetary boundaries. But if you Google Johan Rockstrom, you're going to find it. He's a Swedish guy. Now, what he did is he identified what he called planetary boundaries. 9 things about the environment that relate to practices that may or may not be sustainable. And also, he refers to how bad is it? Here's something that we're doing to our environment, or a problem in the environment that we can identify. How big of a problem is it? And is it getting worse? That's what the diagram does. I added the little pictures. In the middle, we see the Earth. Around the Earth, we have one ring here, and then a second ring in dotted lines, and then a third ring. Anything that is within that first ring is considered a safe situation. Sure, it can be a problem, and it is a problem in some places, possibly, but it's not a problem to the point of imminent danger to the planet. If we're in the second zone right here, yeah, this is becoming a problem, and it could become a much bigger problem. And if we're getting into this third zone and beyond, these are big environmental problems, whether you know it or not, that have to be resolved. And if they don't resolve themselves, then there's big implications for how it could affect us as humanity. How many people can live on Earth, and how healthily can people continue to live on Earth if these environmental problems continue. I'm going to run through those that we can see right here. The first one is kind of it's almost a success story, is ozone layer loss. There was a chemical conference, a press conference at a chemical conference many years ago, I think in the 1970s. And there were these chemists, and they had these wonderful new chemicals. And they wanted to demonstrate how safe, how stable the chemicals were. And so the man, it was this kind of a goopy, clear liquid. And the man said, "I'll show you." And he drank a cup of it. And he knew what he was doing, because these chemicals are extremely, chemists would say, inert. They're not reactive. They're really, really non-reactive. And they're chlorofluorocarbons, and in some ways, that is a good thing. They don't interact much with living parts of the environment. But one thing they do, unfortunately, is when they become in a gas form and they go into the atmosphere, they have a very unfortunate effect on a chemical called ozone. Ozone in the upper atmosphere, it's a kind of oxygen. Specifically, it's 3 oxygen atoms in a row, and that's an ozone molecule. Ozone has this special property that when high energy light hits it, like ultraviolet rays or X-rays from the sun, it absorbs that energy versus that energy going through the upper atmosphere and striking the surface of the Earth. That's a bad thing, because those high energy radiation waves from the sun can cause blindness, can cause cancer, among other things. Now, the fortunate part here is that people realized that there was a hole growing in the ozone layer above the Antarctic and above the Arctic, by the way, and they recognized that these chlorofluorocarbons were probably the problem. And in Montreal in 1987, they resolved to say, okay, well, we're just going to get rid of this stuff. And more or less, they have. Related chemicals are still used, but they're much less harmful to the ozone layer. So what we see in that case here is that it's in the safe zone. It's still an environmental problem. There's still an ozone hole, and those chemicals are still out there, and it's still possible to make them again. But it's recognized as a problem, and there's international agreements to address that problem. On the other side of the coin, we have what is arguably a much bigger problem, climate change. Simply put, climate change is an increase in the average temperature of the atmosphere over time. That being said, Normally, when people talk climate change, they're talking about that increase that's happening right now because of excess carbon dioxide going into the atmosphere from our burning fossil fuels. That's the climate change of today. More about that later in my lesson on the greenhouse effect. One thing we see here is that climate change is in this increasing risk category, which should probably match with your daily experience. You probably hear in the news a fair bit, oh, this event, this one, or this event that's happened was made more likely by climate change. This is the language that climatologists, climate scientists use when they talk about natural disasters and climate change, increasing risk. You're hearing that most likely as well. I hope, because this is your generation and your future, I hope you're paying as much attention to it as really you ought to. It's an increasing risk and an increasing problem. Ocean acidification is another side to that. You see, the thing is that we've been burning coal and gasoline and natural gas for well over a century. Eventually we'll run out, but we haven't yet. And when you do this, you're releasing carbon dioxide into the atmosphere. If you've ever drunk a can of soda water, just the bubbly with no flavor, you probably noticed it's got that, as the bubbles pop on your tongue, it's kind of a sour sensation. This is because carbon dioxide, when you pump it into water, it actually makes the water more acidic. It really is an acid. Most of the carbon dioxide that's come out of the tailpipes of cars and of trains is in the ocean. A lot of it is in the atmosphere, yes. It's gone up in levels in the atmosphere, yes. But most of that carbon dioxide has been soaked up by the cold waters of the ocean. And as you might expect, this is not necessarily a good thing. Organisms that need a certain level of acidity in the ocean can be harmed when the ocean becomes more acidic. Organisms specifically that form shells have this it's a particular problem for them. What forms shells? Well, we all know snails and clams do, but more importantly for the living things of the ocean, coral forms a shell. Coral reefs in the tropics are home to many thousands of fish species and other species, and they're in danger in a double threat. One, from oceans becoming more acidic. Two, from ocean surface waters becoming warmer. Climate change is expected to have some very nasty effects on the ocean. The unfortunate thing about the ocean, of course, is none of us actually lives in it. And so we don't witness those changes, and so maybe don't appreciate those changes as much as we should. Possibly this is part of why people tolerate overfishing so much. The other two others here are nitrogen and phosphorus use. The reality is that there are very many more people in the world today than there would be able to be otherwise if we weren't using artificial fertilizers. If you go back to the 19th century, when the fertility that we used to make our crops came from the soil only, the nitrogen and phosphorus in living things, there were a little less than 1 billion people back then. When I was born, there were about 4 billion people in the world. Now we're pushing 8. Part of this, there's a lot of reasons for this. Increasing economic well-being, increasing rates of vaccination, better farming practices. But a huge part of it is artificial fertilizers. Nitrogen fertilizers are made in factories. Phosphorus and potassium and other fertilizers, they come from rock. They don't come from the soil. I specifically am saying they're locked into rock, and we've been able to mine them out from the rock. It used to be that to get phosphorus, the source for that were these islands off the coast of South America. They were so important, there was actually a war over them, the Guano War. These islands are basically stacks of bird dung. And I'm talking about tens of meters thick of the stuff. And there's other islands in the Pacific that are the same way. Seabird droppings from over the thousands of years accumulated and made this rich source of nitrogen and phosphorus. So rich a source that people were willing to fight wars over it. Well, they don't fight those wars anymore because today there's much better, easier sources of those minerals than any kind of guano islands. Because there's so many sources of natural nutrients, that are needed for food, this has allowed human populations to increase substantially. We can make more food, and so there can be more of us. Now, of course, people might well argue that population increase that's coming as a result of that has a lot of nasty knock-on effects that are leading to their own, that are pushing these other boundaries, is I guess what I'm trying to say. And let's look right here. Well, with ocean acidification, we're still in the safe zone. Nitrogen and phosphorus, these are not, they're not big ticket items. People don't talk about them very much, but they're actually huge environmental problems. If you go on, say, Google Maps or something like that, and try to Google the Mississippi River Delta, what you're going to see in the delta, and then in the the offshore streams, like from the delta into the ocean, you'll see it's a much paler color than the surrounding ocean water in the Gulf of Mexico. What that reflects is the fact that there's so much agriculture in the upstream Mississippi River basin. A massive portion of the Earth's food is made there in the central United States. But excess fertilizers do make it into the water. They do make it into the Mississippi drainage. They're carried to the ocean, and they still keep doing their thing once they've reached the ocean. They still are able to fertilize the growth of animals, tiny animals in the Pacific, it's the Gulf of Mexico, it's the Atlantic. And this is not necessarily a good thing. Because what can happen is, with all that nitrogen and phosphorus, tiny animals can grow on the surface only, but when they die, they sink to the bottom. Bacteria eat the dead things up further to the bottom. The bacteria are able to use the oxygen and take up all the oxygen. But then what happens is other bacteria can still survive and keep doing the breakdown that don't even need oxygen at all. So the oxygen levels can go way down in the water because of the fertilizers. The fertilizers, you might think, oh, they'll be good for life everywhere, but in actual fact, they're not. This is why nitrogen and phosphorus use are beyond that higher risk zone, because it's easy to demonstrate that we're using too much fertilizers for our for the natural environment. If you consider that salmon water, if we were doing the same thing to our water in, say, the Skeena River drainage, as is done in the Mississippi Delta, and our water had so many nutrients in it, had the same kind of levels of agricultural output, well, we wouldn't have any salmon, is the bottom line. These nutrient cycles affect the living things in the water in a negative way. Next is freshwater use. This is an interesting one, because notice that according to Rockstrom's boundaries, we're still in the safe zone. We're fine for water. The thing is, that's a global figure. If you look at a map of Canada, you'll see that Canada it's peppered with lakes and rivers. Canada's north is just a continuous landscape of giant lakes. If you look across the ocean, across the Arctic Ocean to Russia, you'll see the same thing. Huge amounts of fresh water just spilling into the Arctic Ocean and into the Pacific Ocean. Other countries in the world have vast amounts of fresh water as well. Congo River carries a massive amount, even tropical Africa carries a lot of fresh water into the ocean. So does the Amazon. Many of the great rivers of the world are still flowing into the ocean, and everything's just fine. There's enough fresh water to continue, in fact, more fresh water could be drawn from those rivers. But there are other rivers in the world, like the Pearl River, like the Colorado River, that are just a trickle of their former selves. Giant watersheds that should be carrying Fraser River-size amounts of water into the ocean. I'm hoping you've been to the Fraser, so you'll know what I mean. It's a big river that should be carrying that kind of level of water outflow into the ocean, but are carrying an amount smaller than the Bulkley River, because most of that water is being used upstream, being used in rice paddies, being used in manufacturing, being used in other forms of agriculture, being used by people. Other countries, like, say, countries in Central Africa and Central Asia, they've got their own problems. The thing is, if you're in, say, Turkmenistan or Niger, you're not anywhere near the ocean. And so clouds are not carrying water far enough inland to rain on your country. They depend on groundwater, which you can run out of because it's not sustainable. It's not a renewable resource. And they depend on precipitation. But they don't get enough of that. And so there are many parts of the world where fresh water is actually in extremely short supply. There was a city in South Africa. There was a city in South Africa called Cape Town that was almost out of water. Imagine a city the size of Vancouver where you get, a couple of liters of water per day per person. And they were at a point where the reservoir was literally almost dry. The irony being that this is actually a city that's located on the ocean. Since then, it has rained, but, it could then stop raining again, right? Fresh water is not evenly distributed on the surface of the earth. We're in a safe zone globally, not so locally. Land system change is a huge one. And, of course, it drives a lot of the other problems we're seeing here. Some of you might have heard of a guy named Jair Bolsonaro, president of Brazil. He has as good as declared the Amazon rainforest as his enemy. As far as he's concerned, the Amazon, one of the great wildernesses of the earth, and very important for our various matter cycles we're going to look at in this unit, he considers it an enemy to economic progress. He would much rather that forest be converted to cattle ranches and to soybean farms. And, of course, it's easy to be critical, very easy to be critical, but at the same time, if we look here in Canada, we have converted huge amounts of our forested land to other uses. If you look in the States, where they have 10 times the population of ours, they once had forests that covered I think there was an expression that a squirrel could have run from Kentucky all the way to New York, from one tree to another. There was a continuous amount of tract of forest in the eastern United States, which is now almost all gone. People live there now. Bolsonaro might well say, well, look, we just want economic progress like the rest of you. The sad reality is that this economic progress brings with it a great cost of a loss of wilderness. And we see here, by Rockstrom's say-so, we're not in the safe zone anymore. It's in a zone of increasing risk. Connected with that is extinction. I was thinking, what little picture am I going to draw to make the extinction memorable? Where, notice with extinction, we're in the highest level of risk of any of them. And I thought, well, should I do a tiger? Should I do a dodo? I think what I want you to know about extinction is that most of it, you never hear about it. Species are going extinct at thousands of times the rate that new species come into existence. This is a huge problem. There's some million or maybe 10 million species on the Earth. I can't remember the figure. I think it might be one getting extinct per day. I need to look that one up. But it takes thousands of years for a new species to come into existence. So species are going extinct far faster than new species can come into existence. and any wilderness that is available for that new species to come into existence in the first place is being lost with land system change. It's a huge problem. So what do I draw to illustrate extinction? To show you that it's most extinction you don't hear about, I draw you an Oahu land snail. Probably a lot of you have been to Hawaii. Hawaii is a beautiful place, but it's also kind of a graveyard for extinction, a museum of extinction. I don't know what expression I'm looking for. A lot of species have gone extinct in Hawaii, and there's been a lot of really tragic reasons for that. When the first settlers arrived in Hawaii, there were very few insects. There were plants everywhere, but very few insects. Well, there had to be something to fill the gap for plant-eating organisms in that ecosystem. So because there weren't so many plant-eating insects, there were snails. Hundreds of species of land snails evolved in Hawaii. We hear a lot about or at least some about the extinct birds of Hawaii, but there were way more species of land snails, and they're in a terrible spot. In fact, land snails all across the Pacific Islands have gone extinct for really, unfortunately, a lot of very avoidable reasons. The Oahu land snail and many similar species, how did it go extinct? Well, there was a species called the African giant snail, and it had been introduced to Hawaii by someone, I don't know who. It was becoming a huge problem for the crops because there was nothing to eat the land snail. How about we bring in something that'll eat the land snail? So they tried different things, and they eventually settled on the rosy wolf snail. The thing about the rosy wolf snail is it found the native snails a lot more palatable, and so it would find the tracks of the snails. You know how snails leave the little slime tracks? What it would do is it would go along and would find a slime track for one of the native snails, locate the slime track, and then boom. These things are large enough and fierce enough, they're able to swallow the native snails whole. So most extinction you don't hear about, but it's still tragic at a lot of levels, and you might think, well, I don't really care, they're just snails. The thing is this, that many of the other services that are provided by ecosystems, there has been evidence that you need to have a certain diversity of species in your ecosystem in the first place. That if you run out of species, or certain very important what are called keystone species get lost, then the environment can change in unpredictable and radical ways. So you might not think you need these species, but for feeding into other ecosystem services, it turns out that you actually do. And will we know, how many species can we lose? Which species can we replace them with, potentially? See, there's problems with that. It's often unknown. Sure, some species can go extinct and it won't affect your life. But if this keeps happening again and again and again, then it does get to be a problem. The analogy that is made for species extinction, is why it's a problem, is we imagine a jetliner. And the jetliner is flying through the sky, and jetliners have got all kinds of rivets and parts to them. And if you take off one rivet, then you're fine. The jetliner's not going to fall out of the sky because it lost a single rivet. But you keep taking them out one at a time, and eventually, well, it loses air pressure, or the engine falls off, or something tragic like that. The point is, eventually, if you remove enough species from an ecosystem, then there get to be some major effects on the services the ecosystem can provide. So this is the explanation, and I guess a really abstract explanation for you, for why extinction is such a big problem. And of course, for a lot of people, it's just really sad. They would prefer, if they went to Hawaii, to be able to see a bunch of pretty snails on the bush, rather than just a bush or a predatory snail or something. The other two here are unknown entities. This is kind of recognizing the fact that there might be threats to the environment we don't even know about that might arise in the future. We just don't know what they are yet. If I had said to you, if I talked to you last year about COVID, a year ago about COVID, You wouldn't have known about it. I didn't know about it. It was an unknown entity back then, but look where we are now. And the last is atmospheric aerosols. I think what I'll do is I'll get into that in the next lesson. So I hope that this helps for understanding ecosystem services and planetary boundaries. I'll just zero in on these real quick. So that. Right. Okay. Bye for now.